Welcome, guys. So this video, we are trying to show this fact. So the transpose inverse map. Maybe this is the first time you guys hear about this. Okay, so it's inner automorphism of a special linear group. So we will prove this fact and talking about what is the meaning of it. Okay, so now we need to explain word by word. So the settings that given a general linear group, so with the coefficient z. So basically this is the n by n matrices, but with coefficient z, and the determinant of this, let's say x, is non-zero. So x belongs to n by n z. Okay, and the transpose inverse map is the special map. Basically, it can map from a general linear group Z to general linear group Z by just mapping this alpha to so given the n by matrices, we can just take a inverse, take a transpose and do the inverse. Basically, everybody knows about linear algebra, so it's the same as you do the inverse and do the transpose. Okay, and it's obviously that this is the well-defined map because the determinant of G, this alpha is still non-zero. Okay. Right, but yeah. Okay, so but the problem is that although the determinant alpha T inverse is 1 over determinant alpha, but the problem is that this is general linear group with coefficient z, right? So basically this should be z, right? But this is only happen when the determinant alpha is basically plus or minus 1. So actually this map is not well defined from GLNZ to GLNZ. It should be only defined on the determinant 1 part. Okay, so that means the transpose inverse map can define to be a map, basically given a special linear group with coefficient z. So basically this is the determinant 1 part mapped to determinant 1 part, and now it's well defined, just given alpha from alpha inverse t, and obvious that determinant alpha is also 1, and then this is also 1. Okay, so now we understand this transpose map. We understand this special orthogonal group with degree 2. Degree 2 means n equals to 2. Okay, so this fact is that the transpose inverse map is an inner automorphism. Okay, so what is the inner automorphism? So given a group G, right? Given a group G, we can construct all the bijective homomorphism from G to G. So basically, all of it is called the automorphism group of G. So basically, this is the F from G to G, which is bijective, and also the homomorphism. Yeah. So this is also a group. It's a group. Okay. So one special subgroup of it is inner automorphism. Basically, the inner automorphism is the F, right, labeled by G, which is by the way, G is BG. So this FG is well defined. If somebody gives you H in a group, right, you just define to be G inverse, right? So this is the very natural. That's the inner automorphism. Just given basically each G, right, will construct a group. I will construct a set in this. Okay, so basically this is very natural, right? So this fact says that the transpose inverse map is an inner automorphism of special linear group of degree 2. So basically, say that this map is actually the inner automorphism of special linear group. So basically, we need to prove, we need to find something, right? We need to find such G to make that this is the inner automorphism. Okay, so now we can prove. So the proof is simple. Let's take maybe, so we just take a maybe x to be ABCD, and this is as 2z, And we can prove its inverse is basically this one. Okay, and also its transpose is just direct computation. Okay, so the xt inverse is just this one. Okay, so then we can let's take the I to be maybe here, maybe this one. Okay, and okay, so we compute like ix, right? So ix is just this, right? So we just do the direct computation a b c d. So ix just minus c minus d a b. Okay, and then we compute ixi. So this is this. Sorry. So yeah, basically we do the same thing. Okay, so this is minus d, and yeah, so this one, so it's c, and this is b minus b, right? So this is b and minus a. Okay, so sorry. So basically, sorry about it. So we need to compute. Sorry, yeah, because this is G inverse, right? So I should compute this. I should compute inverse of this. So inverse. So we can see here we get this is yeah. So this is inverse is just this, right? So what we have now is this d and minus c and minus b and a. Okay, so we can see these two are the same, right? So that means this xt inverse is basically ixi inverse for all x belongs to 2z. Okay, so this shows that the transpose inverse map, right, is indeed the inner automorphism due to this I. Okay, that's it. I will see you guys in the next video. Be sure to subscribe to my channel. Thanks.